I'm going to do problem 3.12 from Horton's 5th edition. I'm calling this part 1 because it may take so long that I need 2 parts to the video. Let me read the question. So the question reads, the titration curve for histidine is shown below. The pK values are 1.8 for the carboxylic group, 6.0 for the side chain, and 9.3 for the amino. Then a titration curve is there. And then there's a series of questions A through F. Draw the structure at each stage of ionization, identify points on the titration curve, identify point at which pH equals pK. So I'm going to leave a place here for the titration curve. Let me show you. So 1, 2, 3 equivalents of base, and half equivalent 1.5, 2.5. So this is equivalence of base, not molarity of base or moles of base or concentration or volume, but equivalence, and that's typical for a biochemist to think in terms of equivalence. And we have 2, 4, 6, 8, 10, and 12, which we don't need. I'm going to start this problem by drawing the molecule that's being titrated. Because it's a base titration, and we see that the first point on the plot is here, which it means that the molecule is fully ionized, is fully protonated. So let me draw it here so we know what we're talking about. I'm going to draw it longhand, and I'll try to keep it relatively small. So the form that we expect to be titrated will be fully protonated. The amino group is protonated, the histidine is protonated, the side chain, the imidazole, the side chain is protonated, and the carboxylic acid end is protonated. So this molecule has a net charge of +2, so presumably it's sold as a salt. Perhaps it's a sulfate salt, or perhaps it's a dichloride, but this is what we'd be starting with. And then it's going to ionize. What's the most acidic group to ionize is going to be the carboxylic acid part, and the pK of it is 1.8. So next we will, when that is neutralized, then we will have this form where this is positive, this is negative, and the imidazole group is still protonated. Then the next equivalent of base will deprotonate that, and using the question's instructions, we see that the pK of this next ionization is going to be 6, and that's going to be the imidazolium. So we still have the 3 protons on the amino. They're carboxyl, still carboxylate. And now we have this imidazolium group, and the pKa's, where I have it drawn here, there's a proton in each nitrogen, and the pKa's are slightly different. Remember, this is a delocalized aromatic system, and so the charge is delocalized, and either one of these protons can be released. The pKa's are not that different when there's a choice between them. Once it's ionized, then it won't ionize again. So the pK we're talking about here is the pK of this group, and it will only ionize once. Once that has been neutralized with two equivalents. We still have a positive charge here. So this molecule, let me go back here. So the molecule here is in a 2+ form. Here there's plus, negative, plus. So we have a 1+ form. Now we have, I keep on leaving out these charges, a neutral form. And now the last proton, so which proton was it? It was this proton, then it was this proton, and now it's going to be one of these protons. And the fully titrated form will be this form, where the amino is neutral, the carboxyl is negative, and the imidazole side chain of histidine is now also neutral. So I did something wrong here. That's right, just not very well drawn. Okay, so this part is neutral. This other one does not ionize. This other proton does not ionize at pHs we care about. So this form now has one negative charge and no positive charges, so it's -1. And the pKa here of this last ionization, according to the problem, is 9.3. So we have 4 forms of histidine governed by 3 pKa's, and we want to look at the ionization curve. So first I'm going to draw it. If I look at this, I see it starts out about pH 1. After half an equivalent, we have something near pH 2. At 1 equivalent, we have something near pH 4. I forgot to label these. 4, 6, 8, 10, 12 is pH. At 1.5, we have something near 6. At 2, we have something near 7. At 2.5, and this is 1, 2, 3. At 2.5, we have something near 8. And at 3, we have something, it's maybe closer to 9. At 3, we have something near 10. And then the curve we show is this: fast, slow, and going up. I didn't draw that very accurately, but nonetheless, that's the shape good enough for us. So what's going on here? If we add one equivalent of base, if we start with this molecule, we start here, and we add one equivalent of base, we convert one equivalent to this form. So that's the first equivalent of base. And then another equivalent of base, we have this. So the second equivalent of base creates that, and the third equivalent of base creates this. So that means we have, at this starting point, the 2+ form. So I'll do that. After one equivalent here, we have the 1+ form. So let me do it. I'll put it above. ++. After, that's here. Here, after one equivalent, we have 1+. After 2 equivalents, we have a neutral form. So this would be the neutral form. And after 3 equivalents, we would have the negative form. The book also asks us, what about after half an equivalent, or 1.5 equivalents, or 2.5 equivalents? And here what we would have then, at this point we would have equal 2+, we would have a mixture between 2+ and 1+ in equal ratio. So at the pKa, after half an equivalent, we have, this is how a buffer works too, half of it is in this form and half of it is this form, and that's going to be then at pH 1.8, it's pKa, because at the pKa, at the pH, when the pH is equal to the pKa, the two forms are equal. At 1.5 equivalents, here we're going to have 1 and then equal between the plus. So we're going to have 1+ and the neutral form are equal. So it's going to be poised between these two, and that's at pH 6.6 here. So we expect then After half an equivalent, this goes over to 1.8. After 1.5, this goes over to 6. And after 2.5, we'd expect it to be the third pKa, which is 9.3. So at this form, at this point here, 2.5 equivalents, you should be equally neutral and equally -1. So I think we've answered all the questions. Let me see. Draw this structure of histidine at each stage of ionization. Yes. Identify points on the titration curve corresponding to those species. Yes. Identify the points which the average net charge is 2 plus 5. We've done all of that. Identify the point at which the pH equals the pKa of the side chain. So which one is that? The side chain ionization is this one. So where does this happen? This is going to be after 1.5 equivalents. So that's here, and that's 6. So after 1.5 equivalents, we will have equal amount of protonated and unprotonated side chain, and that's at the pH equal to the pKa. So it's 6.0. Identify the point that indicates complete titration of the side chain. Well, that's 2 equivalents. That's fine. That's when it's neutral. So 2 equivalents. That's here. We've looked at that. And at what pH ranges would histidine be a good buffer? So in general, what we care that remember let's look at this pKa plus log of the concentration of the conjugate base over the acid. So anytime the buffer is greatest is when the two forms are equal to each other. Because at this point, what happens? At this point, let's say here, if base is added, then it resists the change of that. If acid is added, it resists the change. So if we, let me put it this way, if we're equal amounts of this form and this form, then any acid added to the system can be absorbed by this form, and any base added to this system is this. So we see that when the forms are equal at half an equivalent, the rate of change of pH with respect to equivalence of base is slow. So it changes slowly, and until it's all one form, then it's changing very fast. There's an inflection point is at 1 equivalent, and then it starts changing slowly again, where there's 2 forms, and then fast and slowly. So we always have a good buffer. Let me write that down. A good buffer for a pH is going to be near the pKa. In this case, we have 3 pKa's. So histidine would be a perfectly fine buffer at pH 1.8 or pH 6.0 or pH 9.3. It would be a very bad buffer then when it's fully protonated, so a pH well below, let's say pH 1. It'd be a bad buffer here in between pH 4, and it'd be bad in between this, which would be halfway between those two. So what is that? It's going to be about pH 7 point. We can even calculate that. 9.3 minus 6 is 3.3. Half of that, let's say, is 1.6, so 7.6. So it'd be a bad buffer at 7.6. 7.6. So it's a good buffer where this line is flat, and a bad buffer where this line is steep, which is anywhere before, in between, and after. I think that answers all the questions, though not in the same order.